You have stood in front of cracked concrete 100 times, your driveway, a parking garage, a bridge on your commute. You probably assumed it was normal. Concrete cracks. That is what concrete does, but some of the oldest concrete on Earth has never cracked at all. In this video, we are going to look at why, and at a real, well-documented chemical additive that has been quietly used by some builders for centuries while the mainstream industry moved in a different direction entirely. The missing ingredient. Modern Portland cement, patented by Joseph Aston in 1824, hardens through a chemical reaction with water. That reaction leaves behind a byproduct called calcium hydroxide, a relatively weak compound compared to the rest of the cured cement matrix. Over time, water penetrates the slab, reaches that byproduct, and during freeze-thaw cycles, the expansion and contraction creates the cracking most of us consider completely normal for concrete to do. There is a class of additives called pozzolans, finely ground minerals that react chemically with that leftover calcium hydroxide instead of leaving it sitting there as a weak point in the structure. One of the most studied pozzolans is metakaolin, produced by calcining kaolin clay at high temperature, typically in the range of 700 to 800 degrees Celsius. When metakaolin is present in a concrete mix, it consumes the calcium hydroxide through a chemical process called the pozzolanic reaction and converts it into additional calcium silicate hydrate, the same compound primarily responsible for concrete strength in the first place. The result, supported by genuine materials science research conducted over several decades, is concrete that can become denser and more water-resistant over time rather than progressively more porous. This is not fringe chemistry. Metakaolin and other pozzolans, including fly ash and silica fume, are recognized supplementary cementitious materials studied extensively in civil engineering literature and used today in specialty and high-performance concrete applications, bridge decks, marine structures, and high-strength architectural concrete among them. They remain a small fraction of total global cement production, largely for reasons of cost, supply chain infrastructure, and long-standing industry habit, rather than any coordinated effort to suppress them. The Roman example. To see what pozzolan-based concrete can do over very long timescales, look at Rome. The Pantheon's dome, the largest unreinforced concrete dome ever built, has stood for roughly 1,900 years. Roman harbor structures have survived 2 millennia of constant saltwater immersion. For a long time, the durability of Roman concrete was something of an open question in materials science. In 2023, a research team that included scientists from MIT published findings explaining at least part of the mechanism. The Romans used a hot mixing process, combining volcanic ash with quicklime at high temperatures. This created small calcium-rich deposits called lime clasts, distributed throughout the concrete. When a crack later forms and water reaches one of these deposits, a reaction occurs that produces new mineral growth, partially healing the crack from within. This is genuine, peer-reviewed, recently published research, not a buried secret. It explains a real durability advantage in ancient Roman concrete that differs meaningfully from how most modern Portland cement behaves. Smeaton's Lighthouse. There is also a well-documented 18th century English example worth knowing. John Smeaton, an English civil engineer, was tasked with building the Eddystone Lighthouse off the coast of Cornwall, a structure that needed to withstand constant, violent Atlantic wave action on an isolated offshore rock. In the 1750s, Smeaton experimented extensively with hydraulic lime mixed with pozzolanic materials, including volcanic ash imported from Italy, and found a formulation that hardened reliably even in wet marine conditions, at a time when most conventional lime mortars failed or washed out in that environment before fully curing. His lighthouse, completed in 1759, stood for over a century before being decommissioned, not because the structure itself failed, but because the rock formation it was built on had begun to erode beneath it. When it was finally dismantled in the 1870s, reports described the mortar as having become so hard that workers struggled to break it apart by hand. Smeaton published his findings in detail, and his work remains a recognized milestone in the history of hydraulic cement and civil engineering more broadly. His work predates Aspen's Portland cement patent by nearly 70 years. Portland cement ultimately became the dominant building material of the industrial era, primarily because it set faster and was significantly cheaper to produce and transport at scale, a genuine engineering and economic trade-off between speed of construction and certain long-term durability characteristics, rather than a secret suppression of a known superior formula. The Amish practice. There is a real documented practice among some Amish and other traditional builder communities of incorporating finely ground clay additives into farm concrete, a practice with plausible roots in older European masonry traditions carried to North America by various immigrant communities. Some agricultural extension research, including work published by university extension programs, has examined historical farm concrete and found it sometimes performed well over many decades. This is consistent with the broader pozzolanic chemistry described above. It does not require any theory of suppressed knowledge to explain. Pre-industrial and small-scale traditional builders often retain techniques that industrial-scale manufacturing moved away from for reasons of cost and standardization, in masonry as in many other crafts. The pyramid theory, a contested hypothesis. In the late 1970s, French materials scientist Joseph Davidovits proposed a genuinely unconventional theory that at least some of the pyramids at Giza were constructed using an early form of cast geopolymer concrete made from crushed limestone, an alkaline binder, and natron, rather than entirely from quarried and hauled limestone blocks. It is important to be clear about the status of this idea. Davidovits' theory is real, and he has published research and demonstrated geopolymer concrete production in his own laboratory. But the hypothesis is rejected by the overwhelming majority of Egyptologists and most material scientists who have examined the pyramids directly, who point to extensive quarry evidence, tool marks consistent with cutting natural stone, and other physical evidence supporting traditional construction methods. Davidovits' theory remains a minority position, actively debated rather than settled fact. What is not contested is that geopolymer concrete is a real and interesting modern material category, capable of significantly lower carbon emissions than standard Portland cement, a genuinely promising area of materials research, regardless of how the pyramid question is eventually resolved. Why this matters today. The global cement industry produces a substantial share of global carbon dioxide emissions. Commonly cited estimates put cement production at roughly 7 to 8% of human-caused CO2 emissions, making it one of the largest single industrial sources on the planet. Pozzolan-based and geopolymer alternatives generally produce significantly lower emissions per ton than standard Portland cement, because they typically require lower processing temperatures and different raw material inputs. Wider adoption faces real mundane barriers: enormous existing capital investment in Portland cement infrastructure, building codes written around Portland cement's well-characterized properties, and the genuine engineering work required to standardize alternative formulations at the scale modern construction demands. These are significant barriers, but they are the ordinary kind that slow the adoption of many beneficial new materials and technologies, not evidence of a coordinated effort to bury a known cure. The chemistry behind durable, crack-resistant concrete is real, documented, and still actively studied today by civil engineers and materials scientists around the world. The real story here is less dramatic than a cover-up, but more genuinely interesting. A slow, ongoing process of rediscovering and re-engineering chemistry that... Like and subscribe for more deep dives into the engineering history behind the materials that built the world around us. Thanks for watching.